All right, so today we're going to do a few problems that will use our law of sines, law of cosines, area, and some of our vector things. So we're going to try and apply some of these things to more real-world situations. So our first example is an airplane, and with triangles, with vectors, airplanes are really big. Ships, anything that's moving is big. So the pilot of an airplane needs to detour around a group of thunderstorms. She turns the plane at an angle of 21 degrees from the original path, flies for a while, then turns and eventually rejoins the original path at an angle of 35 degrees, now 70 kilometers from where she left it. How much further did she have to go because of the detour, and what's the area of the region enclosed by the triangle? So first we're going to look at this. And as always when you're doing a word problem, you want to think about what's the key important information. And my important information is she goes around, so she had an angle of 21 from the original path. So let's come up with an original path first. There's the original path for my plane, right? My plane's flying, just like that. Okay? Now at some point here, oh, thunderstorms. Let's make some thunderstorms. Woo, big clouds, lightning, whatever, thunderstorm. So she has to go around. So we're going to exit, right? Oops, exit. Oh, that's not what I wanted to do. We're going to exit our path at an angle of 21 degrees. She's going to fly for a while, and then she's going to come back once she's past the thunderstorm and re-enter at 35 degrees. So where she re-enters is going to be 35 degrees. So my picture is going to look like this. Now I know it's theoretic, it's really impossible to make that sharp corner here or there, but let's for the moment pretend that we can. And so my other side of my triangle is this, and what I know, my other piece of information, is that she re-enters the path 70 kilometers from where she left it, which means that's 70 kilometers from here to there. And the question is, how much farther did she have to go because of this detour? Well, how far she went is this x distance plus this y distance. So if I can find x and y, then I can find how much farther she went. So let's get started now. Which do I use? Law of sines? I can't use regular trig because it's not a right triangle, I don't think. Law of sines, law of cosines. Well, law of cosines is side angle side, which I do not have, or side side side, which I do not have. So we have law of sines. I need a side and the angle opposite. So here's my side. I need the angle opposite. Unfortunately, I do not have it. However, anytime you have two angles of a triangle, you really have the third side. What I need is 180 minus, what is that, 56, and I'm going to get 124. So this angle right up there is 124 degrees. So now I can find my sides. I can set up two different equations, and 170 over sine of 124 is the same as x over the sine of the angle opposite to it, right? And then I can solve that. X is 70 sine 35 over sine 124, which is 70 sine 130. What was that? 70 sine of 35 over 124. Divided by sine of 124. There's my answer, 48. I'm going to store that in alpha x. You never know when you're going to need one of your answers, and if you don't want to have to retype it in, it's always a nice idea to store it. So there's my x right there. Okay. My other thing I need is y, and in this case, law of sines works very similarly. 70 over sine of 124 is y over the sine of the angle opposite to it, which is 21 degrees, and y becomes sine of 21 times 70 over sine of 124. So very similar. So I get 70 sine of 21 this time divided by sine of 124. And there's my answer, and I'm going to store that in alpha y because I can. Okay, so now I have my two sides, but I have to go back and say, have I answered the question? The question is, how much further did she have to go? So the question did not want to know the length of the sides. I just know I needed those sides to figure out how much farther she went. What I need is the sum of these two numbers. Here's where my storing is really handy. So I have y, I can just do that plus, and I've stored my original answer for x right there, and I get 78.688. So how much farther did she go? Well, she would have gone 70 if she could have gone straight, and so the correct answer is 8.689. So 8.69. So now I have answered the question. Kilometers farther. Part B of this was asking for the area of this region. So let's capture all of this. Let's just group it and copy it. And let's go to the next page. We're going to paste it. Now, there's multiple ways that I can actually come up with this. I could use my Harrow's formula, because right now I do have all sides. It doesn't look like that right here, but I really do know all my sides. Otherwise, I can use my 1/2 AB sine of C. I could use the other one too, but I have all those stored. And maybe we should, you could also do area is S minus A, S minus B, S minus C. Any of those where S is your semi-perimeter. I think it's easier and less typing to use this version. And I can pick either angle. The key is that angle C is what is between A and B. So depending on which angle I pick, I would use different sides. For example, my area could be 1/2 if I use the 70, and what did I get for y over here? I got 30.25, right? If I use the 70 and the 30.25, then I need to do sine of 35, because that's the angle in the middle. I could do the same thing with the x. I could also say area is 1/2 70 times whatever that x was, sine of 21. I could even use both x and y and use sine of 124. So I could do any of those, but I think I'm going to go with my first option. So my area is 0.5 times 70 times my y, and then the angle in between there was sine of 35 degrees. There's my area. And I should get the same answer. Let's just check. If I do 0.5 times, oops, I don't want 0.5. Delete 0.5 times 70 times x. And in this case, oops, not recall. What is happening? Times alpha x. Sine of 21. That should give me the same answer as the other one, 607. So either way, there is my area of that triangle. Okay, let's try another problem. So now we have a plane flying through the air at a speed of 375 miles per hour. There's a tailwind blowing at a speed of 45 miles an hour, but at an angle of 28 degrees to the plane's path. The plane's ground speed is the sum of the air velocity and the wind velocity. So how fast the plane is moving, and you add that to how fast. But you're not just going to add the two velocities because of the degree between them. So this is a problem for vectors. So I need different vectors. And I know that because they're not going in exactly the same direction. If you're going in the same direction, you can just add your two speeds, but we are not. So my problem is, here's my plane. My plane is flying. However, we could go forward, but it is going by 375. And so my speed can be seen as my magnitude of my vector. So there's my plane vector. The wind vector is coming from behind, so it's going in the same direction as the plane. It's not a headwind, it's a tailwind, so it's coming at the same direction but a little bit off. And that vector is 28 degrees, or is 45 miles per hour. So that's its magnitude, and the angle in between these two is 28 degrees. Now the actual flight of the plane is going to be somewhere in the middle, right? It's the sum of these two vectors. And when we add vectors, I take my first vector, and it doesn't matter which order, but if I start with the first vector right here and I add the second, the motion overall is the same as starting at the start of my first and ending at the very end of where I go if I did my first vector. So this vector, and then I did this motion. So I want to combine those two motions into one motion, and that motion more or less is that. Now that's a little bit of a, not the best picture, but you get the idea. So I know that this 45 goes right there. And the key to this, because what I want now is I want the magnitude of that vector, because that will tell me how many miles per hour the plane is actually moving. So the plane's flying like this, but the wind is blowing it. And so overall, the plane's going to move on that trajectory. What I need to do this is right now, because remember, the 28 degrees is to this right there. So I do not have this angle of my triangle. I don't have any of the angles of my triangle, except for the fact that I know that this vector addition always makes this lovely parallelogram. And if this corner in the, or angle in the corner is 28, this angle down here must be supplementary. So it's going to be 152 degrees. And now I can use my law of cosines, because I have side, angle, side. And so x squared is 375 squared plus 45 squared minus 2 times 375 times 45 cosine of that 152 degrees. And we can do all that out. 375 squared plus 45 squared minus 2 times 375 times 45 cosine of 152. And that is an enormous answer, which does not seem to be as fast as it could go, but that's because that is the square of my speed. So my final step is to square root that answer. And 415 miles per hour sounds much more reasonable. So there's my answer. Now the second question that we're asking is what angle to the plane's path is its actual motion? So if I think back to this picture, so here's how the plane's original path, and the actual motion is the red line. So what I want is that angle right in there. So if I think about this picture, and let's redraw it. So I have my 375, I have 45, I have 152, and I want that angle right there. Now it is possible to use law of sines, however I am not the biggest law of sines person because of the ambiguous case. So in my mind it's a better idea to use law of cosines, although you can use law of sines. But I want y, so I'm going to say that cosine of y, excuse me, and what's important with the law of cosines is that whichever angle I'm looking for, I start with that side opposite. So I'm going to have my 45 squared minus 375 squared minus, that was my answer I just got, so I'm just going to say answer squared over negative 2 times 375 times that answer. We know that answer was, what was it? Oh, I can see it here, 415. So I'm going to use this, and I'm going to start again with the, and parentheses are important. I want to take the whole top and divide by the entire bottom. I'm going to take my answer squared. So I take that whole top and I divide by the entire bottom in one piece. And I get this answer, 0.998, which seems extremely small for an angle, but we have to remember that is not the angle, that is the cosine of the angle. So my last step is to inverse cosine that angle. And what I love about inverse cosine in triangles is that you never have to worry that there is a different answer. So there is my answer for part B, is 2.916. So the effect of the wind is to push it 2.916 off of the course it is intending to fly. Okay, let's look at one last problem. This one is all about a spaceship is being pulled by several objects. So one is the engine is actually pushing it with a force of 50 newtons, and that's at an angle of 35 degrees. We're assuming all these angles are from standard position. The sun is pulling it on it with a force of 80 newtons at an angle of 120 degrees, and Mars is pulling on the spaceship with a force of 30 newtons at an angle of 310 degrees. So I have three questions. What's the resultant force is a sum of two components. What is the magnitude of the force, and what direction will the spaceship move? So let's look at the first question first. And the tricky part here is that if I actually drew these three vectors out, because all these can be represented by vectors, and tried to add them up, I would have a mess of triangles. I could add 2 and get a resultant vector and then try and find a new vector. But the cool part is with our little component equation, right? My vector is the magnitude of the vector cosine theta in the I direction plus the magnitude of the vector sine of theta in the j direction. With that little shortcut, it is very easy to take 3, 4, 5 component or 5 vectors all acting on the same object and add them up easily. So my overall vector, the vector that's the result of the sun plus the engine plus the moon. So if I just think about the I part for each, because when you add vectors in component form, you add up your I parts. You add your horizontal vectors and you add your vertical vectors because they're all headed in the same direction. If I have a vector that's 4 in one direction and I have another vector that's 10, when I add them up, I get one overall vector that's going to be 14. Now, if they're at an angle, you can't add the numbers like that, but as long as they're in the same direction, you can, which is why components are nice. It breaks up my vector into vectors going the same direction. So let's take a look at this. So the part that comes from the engine is going to be 50 cosine of 35 degrees. And I'm going to add that to the part coming from the sun, 80 cosine of 120 degrees. And I'm going to add that to the part coming from Mars, which is 30 cosine of 310 degrees. Now, all of that is going to give me one number, and that is going to be the length of the I vector overall. And then I can do a very similar thing where I have 50 sine of 35 and 80 sine of 120 and 30 sine of 310. That number that I'm going to get, oops, this is going to be in the j direction. Okay? So that's what I want to do. And I want to type all that into my calculator. So here we go. We got 50 cosine of 35 plus 80 cosine of 120 plus 30 cosine 310. The result of all that, that is my I part right there. And I'm going to store that again. That's my x coordinate for my vector. Okay. Now I can, if I do second enter a couple times, I can get the exact same thing, and I can just go through and replace all my cosines with sines. It might be just as easy to type them in. I don't know. It kind of depends on what you're doing. On a regular calculator, that's not this one, moving back and forth is fairly quick. On this calculator, it's a little slow. But basically, I'm just doing the same thing as before, only now I'm doing all sines, and boom. There's my I vector. So I'm going to store that, or my j vector, in alpha y. So I get this. So overall, as a sum of two components, the overall motion of this spaceship is going to be 20. So I have 20.24 in the I direction, and then 74.98 in the j direction. So overall, if you think about going 20.24 and 74.98, the overall path is going to be that vector right there. And I did that without having to do any triangles whatsoever, which is cool. Next question is magnitude and an angle. Right? Those are the other two things. Once I have this and I want to find the magnitude of the vector, that's the length of the hypotenuse of this triangle. And so my magnitude of my vector is going to be my 20.24 squared plus 74.98 squared, and I take the square root of that. And if I've stored my variables, that's really easy to do. I'm going to do the square root of x squared plus y squared. Oops, I want that all to be under my square root. Let's try over. Sometimes the newfangled way of doing things is trickier. So I'm going to do, not second, I'm going to do alpha x squared. There we go, plus alpha y squared. That's the magnitude of that vector. So it'll be 77.6 newtons. And then to figure out the angle, right? So my magnitude (77.66 newtons), and my direction, again, if you think about this angle, well, tangent of theta is 74.98 over 20.24, and so my angle is going to be inverse tan of that y divided by x, and I get 74.89 degrees. Now, you want to be careful with this. In this case, that works out. I look at my picture. Does that angle look like it's 74.89? Yes, it does. So my angle is 74.89 degrees. However, if my vectors if I would have had a negative vector, say, if my x would have been negative, and overall my motion would have been this way, and I do my inverse tan, it would have given me negative 74.89, right? If I inverse tan negative 74.98. Wow, those are really close. That's kind of funny. Over 20.24. Right? I would get the negative answer, and then I'd need to add 180. But so there's some word problems. I know it's a little long, but you'll have some problems to do in class, and hopefully this might help if you get stuck.